Hi, this is Professor Stugard, and in this video we're going to be discussing triple integrals. Now, the nice part is if you can do double integrals, you can probably do triple integrals. And if you can do double integrals, well, that probably means you can do single integrals. And so really the toughest part is probably going to be remembering all of your integration techniques from previous calculus courses. The only new part is going to be making sure that we set up our triple integral in the correct manner. Now, before we do that, let's talk about what a triple integral actually is. So the main idea behind a triple integral is that we take some solid region or some box in 3 space, all right, and typically we represent our boxes with the variable capital B, or if it's just a general solid region, we denote it capital E. And it's very important to notice that I am saying the solid region E. So even if we have a surface, right, like a sphere, right, and we talked about spheres, like let's say we have the unit sphere, which is x squared plus y squared plus z squared equals 1. This only represents the outside surface, all right? And so we have our surface as S. When we're doing triple integrals, we're talking about solids. So it wouldn't just be the sphere, which is the outside surface, it would be the entire inside as well. All right, so think about it as the difference between a baseball as a solid or a balloon, which is empty, right? The baseball, which is solid, that's my solid E. There's material all on the inside, whereas a balloon is empty on the inside. All it is its surface. All right. So when we do triple integrals, we're talking about solids, right? We're talking about objects in space that are solid, that have the interior filled in. All right. And when we do triple integrals, what we're doing is we're trying to subdivide that solid region into, well, sub boxes. All right. And when we separate into these sub boxes, almost like, turning into tiny little cubes, each one of those little boxes is going to have a volume, delta V, which is equal to, well, delta X times delta Y times delta Z, which is just, again, the volume of a box, the height times the width times the length. All right. Now, what we're going to do is to have some function, f of x, y, and z, and what we're going to do is evaluate that function for a sample point inside of each of those boxes. Now, this is calculus, so we're going to use infinitely many, infinitesimally small boxes when we're doing this, which means we're going to actually evaluate this function for every single point inside my solid. All right, so what we've done so far, when we've integrated over surfaces, right, with a surface integral, we're evaluating at every point on the surface. With a triple integral, we're evaluating for every single point inside that solid. Then to, again, set this up as a triple integral, because we're doing things infinitesimally small but infinitely many times, we're using our integral notation, and these are going to get scaled by now dv, and, well, the integral means we're adding them together. Now, to systematically ensure that we actually evaluate at every single point, we're going to need a triple Riemann sum, which of course turns into a triple integral notation. And again, this means we're going to have to, again, come up with a systematic or algorithmic way to make sure that we hit every single ordered triple in space, right? Every single point inside that solid by basically going down the rows and the columns and the height. Now, for the easiest type of triple integral, which is just over a box, our triple integral over a box B, again, we typically denote that with the interval for the x's being given between a and b. So the interval for x is a and b. And again, we can kind of see the way that this is set up. We have our triple integral over our region B, and then the x is bounded by a and b. Again, just the same way we did over rectangles in our double integrals. Then the variable y is going to be bounded between c and d, again, constants, which we see in our limits of integration here. So again, this is the iterated integral part, where we're doing integrals inside of integrals. And then really the only difference with the box is now we also have bounds for the variable z. Now the bounds for our variable z are going to be given as s and r, because, well, we kind of ran out of letters here, right? If I kept going in alphabetical order, it would be e and f, but well, we use f for our functions, so we can't really do that. So we have to switch it up to s and r. But again, we see that those become my bounds for z, and that becomes the last part of my iterated integral. And so, again, the nice, neat, compact notation, which is really, really useful, is this. And then typically it'll be your job to plug in those bounds in the correct order. Now, the nice part is Fubini's theorem lets us evaluate iterated integrals like this in any order. As long as our limits of integration are constants, I can evaluate in any order, and I'm still going to get the same result. Now, it's not always going to be that easy, but before we get into that idea, I want to stop and pause for a second, because when we talk about triple integrals, and I'm evaluating it at every single point inside my solid, this very rarely is going to represent a geometric measure like area or volume. And when you think about it, hopefully it starts to make a little bit of sense that, again, when we first introduced our single integrals, right, we're doing a single integral over a single variable x, and we're finding a two-dimensional geometric representation, which is area. When we do a double integral, now we're integrating over two variables, and we're getting a three-dimensional geometric representation in volume. Well, when we do triple integrals, well, now we're doing this over three variables, which means if there was a geometric counterpart, it would be the geometric counterpart in 4 dimensions, which is a little hard for us to wrap our feeble human brains around. So again, the idea is that this integral notation, this summing up functions evaluated at all these points and scaling them, that is, again, typically not bounded by just geometry. And again, we're going to see a lot of other examples, and we've already kind of talked about surface area and arc length being examples of, again, they are geometric ideas, but they're not really the same as area and volume. We're keeping them in the same dimensions. And that's the same idea here with our triple integrals. All right. With that triple integral, we're evaluating every single point in 3 space defined by our solid, defined by our bounds of integration. So we evaluate the function at every single point. We scale it by dv. We scale it by that tiny amount, and then sum our results, infinitely many of them. And so, again, it's not really geometry, but triple integrals are really used typically to calculate things like the center of mass or inertia or different moments, or how gravitational or electric forces are going to affect our objects. What's the overall effect of an electrical field on a particular object sitting in the center based on, well, our function f for that electrical field. That's the main idea behind these triple integrals. So try not to get hung up on the idea of area or volume, because it doesn't really make a ton of sense in the context of our triple integrals this way. Now, when we do have more general bounded solids, right? Not everything is going to be a box. And in fact, very rarely are we just given simple objects like boxes that I want to apply electrical forces to. I'm going to have a way to set up my triple integral. Now, just like our double integrals, our outermost limits, the things that we evaluate last, those have got to be constants. I need to be plugging in numbers as my very last step of this problem, because we should have just numerical results at the end. Again, these are typically problems that are very much related to physics and engineering, where we want a concrete answer. We want a numerical answer at the end. So our last limit of integration must be the constants. Our middle limits of integration can be functions of one variable. And our innermost limits of integration can actually now be functions of 2 variables, which can definitely make our problems a little bit more complicated. It can be a little bit more cumbersome and a little bit more tedious, and you're definitely going to have to pay a lot of attention to how you're writing these things out and organizing your work neatly and making sure that you're not making little mistakes that are typographical in nature instead of actually, well, calculus-based. It's like the worst thing in the world is to be taking a Calculus 3 course, doing all this higher level mathematics, and your mistakes come from the fact that you still are, well, making handwriting mistakes. You're still missing minus signs or exponents, or you forget a variable somewhere. You need to be incredibly, incredibly careful. At this point, organization and handwriting are more important skills than the actual calculus. You should know how to take integrals by now. You should absolutely be comfortable with U substitution and integration by parts and all those integration techniques that you've learned. Right now, it is incredibly important that you are organized and you are neat, because that is where most of the students are going to lose points in this particular section. And if you don't have the discipline to write in neat handwriting and to organize your work, you're going to be in trouble. That has got to be a conscious effort on everyone's part to make sure that your work is neat and organized, and make sure you're not losing points for silly things like thinking a minus sign was a plus. Okay? Now, again, because my first integral that I take, right, I can take the antiderivative, hopefully without too much trouble, like I said, using our techniques. I'm going to be plugging in functions of two variables into that antiderivative. That's where the challenge comes in. There is a lot of algebra that you're going to be doing here as well. All right, so we need to make sure our algebra skills are up to par as well. So again, the idea is our triple integral starts with three variables, x, y, and z. When I do my first iterated integral, the innermost one, I might be down to functions of just two variables. So let's say I eliminate z first, I'd still have x's and y's. Well, then it's a double integral in terms of x's and y's, which is, well, a double integral in terms of x's and y's. You know how to do this already. And then we take that double integral, we do the iterated integral one more time, then it becomes a single integral of just one variable. And we need to do that check at every step to make sure that each time we're getting rid of one of the variables, so that we're not doing a bunch of work and we get to the end of the problem and we're like, oh, wait a second, it's not a number, I must have made a mistake somewhere. So again, work slow, work carefully, and do your best to stay neat and organized. Now, when we are doing our general bounded solids, there are three types. Now, it's not necessarily critical that you remember which one's a type 1, a type 2, or type 3, but it is critical that you understand the main concept here. So with a type 1, that means our z is going to be bounded by functions of x and y. That means that would be our function of two variables, and that's my type 1 region. Now, the idea is that once I do that first iterated integral, once I get rid of the z's, now I just have x's and y's, which means I'm doing a double integral over my region D. All right, my double integral over that region D, now D is in my xy plane. And that's an important thing to keep in mind. As we're taking these triple integrals, the next step is a double integral. And we need to make sure that as we proceed through our problem, that region D is, well, actually a good region that we're going to be able to integrate over. If I cannot integrate over that region D, well, maybe I have to go back a step and redefine how I'm doing this problem. Now, a type 2 is the same idea, except now we have x bounded by a function of y and z, meaning that my region D is going to be a projection into my yz plane. And a type 3 is, again, the same idea, except now y is being bounded, this time by a function of x and z. And so now my projection is in my xz plane. Now, we're going to see as we keep doing these problems that orientation is going to matter, and the fact that it's not going to look exactly the way we kind of expect it to in 2 dimensions as it does in 3 dimensions is definitely going to come back a little bit. But the idea is, again, to just work slow, make sure you understand the entire problem before you try to start throwing a bunch of calculus at it. So let's take a look at an example here. So let's say I want to evaluate the triple integral over my solid region E for yz cosine of x to the 5th dv. And E is my solid defined by every ordered pair x, y, and z such that x is bounded between 0 and 1. Now, first of all, as soon as I see a function that is bounded just by constants, that's bounded only by numbers and is numerically bounded, that is probably going to be my last piece of my iterated integral. That's probably going to be the last step, is to actually plug in those bounds. And then y is bounded between 0 and x. So that's a function. So that could be either the second part or the third part. And z is bounded by x and 2x. So again, that could be the second part or the third part. We don't have any functions of two variables, which is kind of nice, which means it's not going to be necessarily as tedious as some of the problems you'll see in your homework. But now we have to figure out, well, I have these two functions that are both, well, well, I have these two variables that are bounded now by functions of one variable. Which order should I set this up in? Because they're probably going to be interchangeable. Well, this is where we want to figure out, once I do my first iterated integral, what am I going to be left with? And I have two options. If I integrate with respect to z first, and that is what this one on the left is. If I integrate with respect to z first, then my region D ends up on my xy plane. Now, no matter what, we know that x is bounded between 0 and 1. So when I draw my region D on my xy plane, and bounded between 0, bounded between 1, and then y is bounded between 0 and x, or again, the line, right, y equals x. So that gives me a nice neat triangle, and again, that's not going to be bad to integrate over. The other choice is to integrate with respect to y first, and that's what the second one is. Because if I integrate with respect to y first, my two variables left are going to be x and z, so I'm looking at my xz plane. Again, I know x is bounded between 0 and 1, but in this case, z is bounded between x and 2x. So the lines z equals x and z equals 2x, and again, that's my shaded region there as well. When you draw these, you should absolutely be taking the time to make sure that you're writing out what are your variables on each axis, right? My axes are either the xy plane or the xz plane. Take that extra second to make sure you write that in. Okay, so now it comes down to my choice. Which one would I rather do as my double integral? And for me, that's the winner. Now again, it doesn't matter. You could choose the other order and you're still going to get the same answer. But for me, that looks like an easier one to tackle, so that's what I'm going to do. So that means I'm setting up my triple integral now. I'm doing it with respect to z first. I know x has to be last, which by the process of elimination means y is going to be my middle one, right? And so again, that gets substituted directly in at the end in that order. And then I just make sure that my bounds match up as well. So z was the bounds x and 2x, y was the bounds 0 and x's bounds were 0 and 1. So now I can do my iterated integral, which of course is going to start with dz, which means I can factor out everything that's not a z. So if I factor everything that's not a z, now I'm just integrating, well, z dz and evaluating it from x to 2x. All right, so you should pause the video and make sure you're following along and getting the same answer, but hopefully the antiderivative of z with respect to z is automatically in your head as 1/2 z squared. Again, I can factor that 1/2 out because it's a constant as well. And now I just have to evaluate z squared at 2x and x and find that difference. Again, feel free to do this as scrap work, do it on the side. Whichever way is going to ensure that you're not making mistakes or you're not losing symbols or you're not making, again, those silly mistakes that have nothing to do with calculus but just have to do with your handwriting and your organizational ability. Just make sure you get the right answer. So again, pause the video, figure it out, and now I'm going to tell you the answer. Now, when I square the quantity 2x, that's 4x squared. When I square x squared, that's x squared. So the difference is going to be 3x squared. Now I know my second iterated integral is with respect to y. So I'm going to factor out everything that's not a y. So, well, I can factor out now the 3 and the 1/2, so 3/2. I have an x squared and my cosine x to the 5th. And now I need to take the antiderivative of y with respect to y, which should feel familiar. But again, do the work on your own. Pause the video. When you're ready, hit play, because the answer is, of course, 1/2 y squared. Now, again, I'm going to be able to factor that 1/2 out. And then I'm going to have y squared evaluated at x and 0, which gives me x squared minus 0, which is just, well, x squared. And so when I combine all my constants together, 3/2 and 1/2 gives me 3/4. I'm pulling that all the way outside my limits of integration. And then I have an x squared and an x squared, which gives me x to the 4th, and then cosine x to the 5th dx. All right, Now again, you're in Calculus 3, so hopefully at this point this becomes a very obvious antiderivative for us to take. We can see that we're clearly going to be using u substitution. Let u equal your inside term, so u is going to equal x to the 5th, right? Which means du is 5x to the 4th. Match it up, do u substitution however you feel comfortable with. Again, pause the video because I'm going to kind of continue through with the answer. Is that we're going to get 3/20ths, and when we evaluate, we're evaluating sine at 0 and 1. Now, sine of 0 is 0, and sine of 1 is, well, there's not really a nice, neat answer for that. So, again, the exact answer is just going to be 3/20ths sine of 1. The approximate answer as a decimal would then be 0.12622. So that covers all the main ideas behind triple integrals. Again, like I said, organization, neatness is key, and, well, being able to do your regular old antiderivatives. All right. If you have any questions, please, again, email me. Otherwise, good luck studying.